Hi, this is Maggie. In this video, we're going to solve a programming problem that will be easier to solve if we use functional decomposition. Before we get started, I'm going to quickly give you some tips for how to get the most out of this video. First, if you have problem solving with Python, read up through Chapter 5. If you don't have it, you can still learn a lot from this video. Open up idle and follow along with Python as I work. Sometimes I'm going to suggest you pause the video and complete some steps on your own. When I do that, pause the video and do your best to complete the steps on your own. The way to learn to program is by programming. You can watch and learn if you work along with me. Remember, you can always pause the video and try something or go back and watch again. You don't have to wait for me to tell you to pause. There are some automated exercises in the description of this video. The exercises work with the same code or similar code to the code in the video. After you've completed the video, try the exercises to cement the concepts in your mind. Now let's get started. We're going to solve a problem for a friend who wants to create a math game for their cousins in elementary school. The first step in the problem-solving process is to develop a deep enough understanding of this problem that we can define it. To keep this video focused more on development with functions, though, we're going to skip this step in the video and jump to a point where the problem is already clearly defined. Let's go through the game and how the program should appear when it is running. Here's how the game works. There's a board of numbers from 1 to 100. The player rolls a die, getting a value from 1 to 6. Maybe in the future, your friend notes, you could use a die with more sides, such as 10 or 12, to give the cousins practice with larger numbers. For the first move, the player simply moves to the space on the board matching the number rolled. For subsequent moves, the player can move to any space that can be reached by performing addition, subtraction, multiplication, or division on the two numbers, the number that their piece has landed on and the number on the die. They may not move off the board. So, for example, if the user had initially landed on 5, and they rolled a 3, they could move to 5 minus 3, or 2. They could move to 5 plus 3, or 8. And they could move to 5 times 3, or 15. They could not move to 3 minus 5, or negative 2, because that number is off the board. And they could not move to 5 divided by 3, or 3 divided by 5, because neither of those division operations results in an integer. The game should roll the die for the player and keep track of the player's location. Starting with the second turn, the game should roll the die and ask the player where they want to move. Remember, the purpose of the game is for the cousins to practice their arithmetic. It must then confirm that the move is valid, and if it is, move the piece. If it isn't, it should give the player as many tries as they need to come up with a valid move. As a goal in the game should randomly generate a magic number on the board that the player is trying to reach. The game is over when the player reaches the magic number. When the game runs, it begins with a set of instructions that describe the game. Your friend will provide those instructions. For now, the game will begin with the message, "Welcome to the Magic Numbers game" on one line, and on the next, instructions will go here. The game will then report the user's first roll and display the board as 10 rows of 10 numbers, evenly spaced, with asterisks around the magic number and underscores around the player's position. The game will then roll again, report the roll to the user, and ask for their move. It will obtain their move. Their move must be an integer. It will validate that their move can be reached from their location using arithmetic and the roll, and if their move is valid, it will repeat drawing the board and obtaining their move. If it is not valid, it will report, "You can't get to new location from current location with a roll of roll. Try again," substituting in the correct values for new location, current location, and roll. For example, "You can't get to 25 from 15 with a roll of 5. Try again," and it will again prompt for the user's move. This repeats until the user provides a valid move. The entire cycle of obtaining a valid move and moving the piece repeats until the player reaches the magic number. Once they do, the board is drawn one more time with both underscores and asterisks around the magic number, and the message "You reached the magic number" is displayed. The game ends. In understanding this problem, imagine you worked through a number of scenarios with your friend of combinations of valid and invalid moves and different rolls. One short example might be, "Welcome to the magic number game. Instructions will go here. You rolled a 4. The board showing 4 with underscores and 26 with asterisks. You rolled a 2. Where do you move? 26. You can't get to 26 from 4 with a roll of 2. Try again. Where do you move? 8. The board showing 8 with underscores and 26 with asterisks. You rolled a 3. Where do you move? 24. The board showing 24 with underscores and 26 with asterisks. You rolled a 2. Where do you move? 26. The board showing 26 with underscores and asterisks. You reached the magic number. Pause the video and take a moment to think about this problem. Our next step is to identify and select among solutions. Because this video is about functional decomposition, think about ways this problem can be broken into functions, because that is how we will be solving this problem, as that is the skill we need to practice. Most programming problems are so large that they are broken into smaller pieces in one way or another. In functional decomposition, the smaller pieces are functions. Don't worry so much about how the functions will work. For example, we don't know what message is going to be in the instructions, but we might want to put the instructions printing code into a function. That way, if we decide that after a certain number of failed moves the player might need to see the instructions again, we can simply call that function. You could jot down some pseudocode to solve this problem and put the big steps into functions. You could also read over the problem description and look for verbs or actions the program has to take. Those might be good candidates for functions. Pause the video, review the problem, and think about how it can be broken into functions. You don't have to come up with just one solution. Try to come up with different sets of function candidates to choose among. Pause now. How did you do? We had already come up with one potential function, a function to show the instructions to the player, which we might call show instructions. If we work through the problem description looking for actions the program has to perform, we might come up with the following function candidates. Roll die, move player, get player move, validate move, generate magic number, display roll, display board, report invalid move, display final message. What might pseudocode for solution look like using these functions? Probably something like show instructions, roll die, move player, display board, while player not at magic number, roll die, get player move, validate move, while player move not valid, report invalid move, get player move, validate move, move player, display board, display final message. Or perhaps get player move might incorporate the validation to simplify the overall game loop. In that case, we might have for get player move, prompt for move and read in, validate move, while player move not valid, report invalid move, prompt for move and read in, validate move, which simplifies the overall pseudocode to show instructions, roll die, move player, display board, while player not at magic number, roll die, get player move, move player, display board, display final message. For the first version, we might draw an early structure chart that shows the main function invoking all of the other functions. In a structure chart, we draw the function names in boxes, and we draw an arrow from a function to a function it invokes. The structure chart does not show the number of times a function is invoked or order. It also shows data passing, but we haven't considered data yet, so we can start with earlier versions that just show functions and calls, and then move on to adding data as we develop our solution. So we would have main in a box with arrows to boxes with show instructions, roll die, move player, display board, get player move, validate move, report invalid move, and display final message. With the second version, we would draw a structure chart with main in a box with arrows to show instructions, roll die, move player, get player move, display board, and display final message. The get player move box then has arrows to boxes with validate move and report invalid move. In the second version, get player move takes responsibility for both obtaining and validating the move. Before we decide between these solutions, we should think about how data will be represented in this program and what data would need to pass between functions in these solutions. What data do we need to represent? Pause the video and reread the problem description and find values that need to be stored. Pause now. So if we use the sort of blunt instrument of looking for nouns to identify data, we find first board of numbers from 1 to 100. Does that need to be stored? Maybe the range of the board, but the board itself is simply a list of numbers which we can easily generate. We might store min board of 1 and max board of 100. We then have die. We could store a die, meaning the current value of the roll, or if we're thinking of an actual physical die, the value of the face that is up. You might call this die, or you might call this current roll, or just roll. One thing we might consider related to the board is the player's current position. We need to know that so we can validate their move, which will be validated based on the current position and the value on the die. The value of the magic number is something we'll also need to store. That is going to be consistent the entire time the game is being played. There's also instructions, which could be just part of the function that displays the instructions, or it could be a string value that we store. The player's move will have to be stored and validated, and then it will become the player's new position, if valid. We could also consider storing underscores and asterisks as the markers of the player location and magic number location. If those are stored, it will be easy to change them if we want to. Let's start with the data we must store: the player's location, the roll of the die, the magic number, and the player's move. Some of the other data, such as the boundaries of the board, the symbols used for player and magic number, and the instructions, are values we can store and use to make the game more general in the future. In fact, we might also put the number of sides on the die in that category. But for now, we'll solve exactly the problem in front of us and not worry about extensibility. Given the data we have, we should figure out what data each of our functions needs in order to operate, and what values, if any, our functions will return. Pause the video and look at the data we've decided to store and our two different sets of functions, and figure out what data each function needs to operate, and what data each function might produce. Pause now. How did you do? Our definitions for what these functions do might be slightly different, as we haven't defined them formally, so what you came up with and what I come up with might be different. The show instructions function will simply print instructions. If we decided that the instructions were data, we would pass it in, but we are not going to do that at this time, and it returns nothing to the main function. It simply prints to the console. The roll die function will return the roll of the die. It might take the number of sides of the die as a parameter. Now here we have a decision to make. The roll die function would simply consist of a call to randint, and then it would return the result. Is there any reason to make this a separate function if it will consist of only one line of code? There are at least a couple of reasons we might. One is that roll die makes sense in the context of our program, so it might make the program more readable to invoke roll die rather than randint. Another is if we want to hide the implementation details of roll die for some reason. Maybe we think the way that it is implemented might change in the future, so we want to package it away into a function, so it's easy to find the functionality in the program and easy to change. Simply change the one function. Those are the considerations with a simple one-line function like this. In this case, let's leave roll die in for now, for the readability reason, and because we're practicing writing functions. This one can take the number of sides of the die as a parameter and return the roll. In the structure chart, data going in is shown as a labeled data flow. A little ball with an arrow pointing toward the function being called. And data going out is shown as the labeled data flow with the arrow pointing toward the calling function, in this case, main. Now, move player is just changing the value of the variable that is the player's location. Again, it would be one line of code. It's possible that in some future version there might be more to moving a player, but for now it will just make our program more complicated. So that's a potential function I'm going to remove. It's really just an assignment statement. For the board to display, it will need to know the player location and the magic number location, because it shows those values differently with the asterisks and the underscores. So we'll show two data flows going in, labeled with the player location and the magic number. In a future version, if we wanted to change the size of the board, we might pass that in too, but we'll keep it simple for now. What about generating the magic number? Should that be a function? And did we forget that? It's another one-line function, so for now let's not write a function for it. But in a more complicated version of this game, for example, if we had more than one magic number, it might be a function. Now might be a good time to pause the video again, review what we've done so far, and revisit your decisions about the rest of the functions. See if you've changed your mind about the data that's passed and returned in light of what we've decided so far. Pause now. Did you make any changes? It's a good practice to revisit decisions when you have new information. Now let's consider getPlayerMove, validateMove, and report invalidMove. To validate the move, we need to know the location of the player, the die roll, and the move the player wants to make, so let's pass those in. It will return true or false, depending on whether the move is valid, so we might write this as an input validation function and change the name to validMove. The report invalidMove function is another one of those one-line functions. It's just a print statement. For now, let's not consider that a separate function, although again, if we are asked to enhance the program, it could need its own function. The getPlayerMove function is going to obtain a move from the player. I think it's clear that it will return the player's move. What information it needs, though, will depend on which version of the program we write. If we write the more shallow program, where each function is invoked from main, it won't need any data, and in fact, it's a one-line function. If we write the deeper program, where it returns a valid player move, then it will need to know the player's location and the die roll in order to pass that information to the validating function, validMove. Our final function is displayFinalMessage, which is simply a print statement, and at this time does not deserve its own function. Let's remove it. We have two simpler designs to choose from now, and we've determined the functions and the data passed between the functions. The deeper version, with getPlayerMove that returns a validated move, encapsulates all aspects of obtaining a valid player move within one function, getPlayerMove. It therefore simplifies the main function somewhat as well, so this is the version that we will write. Readability and encapsulation are the criteria then that I have used to choose this solution to implement. We're ready to program this solution. At each step in this process, I'm going to ask you to pause the video and see how much of the program you can complete on your own. Starting now, can you write this program on your own, given this design? Pause now. Welcome back. There are many different approaches to writing a program from a design. We could put the structure in place and then flesh out the functions, or we could write individual functions and test each one thoroughly before we write more. Let's work from the pseudocode we wrote before and create a main function that invokes the functions we've planned. We'll start a new Python script and, at the bottom, write a line to invoke the main function. We'll define the main function, def main, open paren, close paren, arrow none, colon, and then we'll put a docstring just under the header, play a magic arithmetic game. Now, working from our pseudocode and our planned functions within main, I will block this out in comments, show the game instructions, roll the die for the first player move, we have move player in our pseudocode, but we are really just going to set the player's location to that first die roll. Display the board to the player. Obtain valid player moves until they reach the magic number. Now, showing the instructions is a function that we planned, so let's invoke that under the first comment. That function won't return anything, so we don't need to assign the result to a variable because there is no result. And let's create that function as well. Recall that we don't have the instructions from our friend, so we'll just write def show instructions, open paren, close paren, arrow, none, colon. And then we'll print, welcome to the magic number game. And we'll print, instructions will go here. And we'll put a docstring below the function header, show the game instructions to the player. Now, at this point, we have something we can test. So let's run the program. We expect to see the instructions and nothing else. And if we run it, that's what we see. Now that we have an outline of our program and one function written, pause the video and see if you can add to this. Any part would be fine. You don't have to develop this in order. If you can't write functions, can you put the function headers in? Pause now. Did you get any other code written? If so, you can compare to mine. Let's move on to the code below the next comment, roll the die for the first player move. We had decided to keep the roll die function in the design, and we decided that it would take the number of sides as a parameter and return the roll. Let's annotate a constant for the number of sides and a variable for the roll. We'll put them at the top of the main function. I'll put a comment below the docstring, annotate and initialize constants and variables. And then I'll write num sides, all caps, because it's a constant of type int equals 6, and roll of type int. Now, below the comment, which says roll the die for the first player move, we'll write roll equals roll die, and in parentheses, we'll pass in num sides. So what's happening there? We're invoking the function roll die, and within parentheses is the data going in. In our structure chart, that's the data flow on the arrow pointing to the function, and it's the number of sides of the die. And the data flow going back to main is the value of the roll, which means the function will return the value of the roll. If we want to use that, we need to assign the return value to a variable, which is why I have roll equals and then the function call. Now, you should write that function. Pause the video and write it. Pause now. How'd you do? Let's go through it together. It doesn't matter what order the functions are in the file, but generally we put functions at the top and then any code that isn't inside a function at the bottom. Mostly we will want all of our code to be in functions, and our only code that isn't in a function is the code that gets the program started, the call to main at the bottom. And as a general rule, have functions that call other functions closer to the bottom. So let's define roll die, and we can put it right below the definition of show instructions. So def roll die, and now we have the parameter list. This function takes one parameter. Again, on the diagram, that's any data flow with an arrow pointing into the function. And in our call within main, we can see that we're passing in the number of sides of the die. So let's call it sides and annotate it to be of type int. So we do dash right angle bracket, which looks like an arrow, and int for the return type, and then the colon. Remember, what is returned is on a data flow pointing back toward the calling function on the structure chart. So I'll write a docstring, return the value of a simulated die roll. And now we're going to need the random library. So up at the top of this program, I'll import random. Within the function, I need to generate a random number between 1 and the parameter value sides. So for example, between 1 and 6, if 6 is passed in as a parameter, and return that value. I can do that all in one step. Return random.randint1, sides. If you're not comfortable with that syntax yet, you can annotate a variable, maybe called roll, of type int, and set roll equal to random.randint1, sides, and then return roll. Once again, we have a program we can test, but it's not going to do anything new because we're not doing anything with the value returned from roll die. We could print it back in main just to show that it's being generated. We'll add print roll back in main after we assign the value to roll from invoking roll die, and then we'll run the program. And now it prints the greeting and instructions message and a random number between 1 and 6. I'm going to remove the print statement. Now, inside the loop, we're actually going to roll the die again at some point, so I'm going to copy and paste that code under the final comment. And this is partly because I'm actually going to change this line of code. That first roll is going to be the player's starting position. So instead of storing it in roll and then copying it into the player's location, another piece of data that we're going to have to store, I should probably just assign directly into the player's location. So up in the variable annotations, I'll annotate player location as an int, and then instead of assigning the first roll die result into roll, I'm going to assign it into player location. I'm going to invoke the display board function under the comment display the board to the player. Once again, pause the video and see if you can both invoke this function and display the board. Pause now. Welcome back. Did you realize that we're missing something? We haven't generated that magic number yet, and we can't display the board without it. Let's do that. I'll annotate a variable magic number, and then I think I'll change this comment to generate the magic number and display the board to the player, as this all feels like part of the setup of the game. To generate the magic number, I'll simply randomly generate a number between 1 and 100. So magic number equals random.randint1, 100. Okay, and now we can display the board. The board displaying function doesn't return anything. What data does it need to do its job? We decided that it needs the player location and the magic number. Now, suppose you don't want to solve this problem right now. You need to think about it. Suppose you just want to keep going with the game and get it playable, and then worry about making the board print nicely. We can do a temporary version of this, almost a stub, that just prints out the player location and the magic number, but doesn't print all of the numbers in rows. Eventually we'll write it, but I want to illustrate that you don't have to solve every problem all at once. You can leave some problems until later, but put some code in to get the program working. So I'll write def display board open paren player int magic number int close paren arrow none and then a docstring. I'll write display the board showing the player's position and the magic number position. And then I'll just format two print statements to identify the player and the magic number, and we'll make that look nice in the future. Let's run it again. And if I run it a few times, and I get player location between 1 and 6, and a magic number between 1 and 100. We're now at the point where we can write the game loop. The game will loop until the player reaches the magic number. Pause the video and write the game loop. Again, it will loop until the player location and magic number are the same. Each time through the loop, it will generate a roll of the die and get a position from the player. Pause now. How'd you do? I hope you were able to get some of this written. We'll write, while player location is not equal to magic number, colon, and then inside we have our die roll. So I can just indent that. And then we need to get the player move. Remember, we're going to write a getPlayerMove function that validates the move. So whatever gets returned from that will be a valid move. And we need to pass in the location of the player and the die roll. So player location equals getPlayerMove, player location roll. Remember that we'll be passing in the current player location because the right side of an assignment statement is evaluated first. And once this function returns, we'll put the return value, the new player location, in the variable player location. And once that's done, we display the board. So we'll copy and paste our display board call into the loop body. That loop is going to execute until the player has reached the magic number. So once we're out of the loop, we know the player has reached the magic number. The condition player location not equal to magic number will be false. So we can print the final message, you reached the magic number. Now, we have only to write the getPlayerMove function, and then we can fix up the displayBoard function, and we'll have a program we can test. So let's see if you can pause the video and write the getPlayerMove function. You will be writing an input validation function as well, validMove. But to develop this incrementally so we can make sure each piece is working before we continue, we can make validMove a stub that always returns true. So I recommend you can start there and then write a proper validMove function that checks if the move the player wants to make can be achieved arithmetically from their current location and the roll. Write the getPlayerMove function. Pause now. How'd that go? I hope you're getting the knack of this and it's all making sense. Let's write the getPlayerMove function together. So, def getPlayerMove, and it takes as parameters player location, an integer, and I'll just call that player, and roll, an integer, and it returns an int, which will be the player's new location. We'll write a docstring comment, return a valid player location from player input. Now, we have some pseudocode for this which we can review. Prompt for the move and read it in, validate, and while it's not valid, tell them it's not valid, prompt for the move and read in. And looking at our sample output, it tells them the roll and asks them, where do we move? So let's start by obtaining the player's move. We'll annotate a variable of type int called move. Now we'll write a comment, obtain the player's move. We'll print you rolled a, and then the value of roll. And we'll use an input statement and prompt for move using where do you move. Now we need to repeat that until we get a valid move. We only repeat if the move is invalid. We'll write an input validation loop using the function validMove, which we haven't written yet. Remember that validMove must take the role, the player location, and the attempted move, and it will return true or false. So we'll write while not validMove, player move role, colon, and then we'll print a message. You can't get to attempted move from a location with a role of role. Try again. And we'll get another move. After the loop, the only way we get out of the loop, or possibly never entered the loop, so the only way we get past the loop is if the move is valid. So we'll write a comment and we'll return move. Now we need to write valid move, and we're going to write a stub that always returns true. So above this function, we'll write def valid move, and we need to make sure we get the order of parameters correct. That's always critically important. The order of parameters in the function definition must match the order of parameters in all calls. Imagine if we tried to call random.randint but passed in the 6-1 instead of 1-6. It would not work. Okay, so I'm just going to copy where I called the function to be sure to get it right. So def, and then I'll paste it in, and I'll annotate the parameters. They're all ints. And the return type is a bool. And we're just going to write return true. But let's put a docstring in that describes what this function is going to do. Return true if move can be reached arithmetically using player and role. Let's run this now and see how our functional decomposition works. So player is 3, and the magic number is 53, and my role is 6. It's not going to check my arithmetic, but let's see if we can continue to move until my position is the same as the magic number. So let me just give a number that isn't the magic number a few times, and then I'll give the magic number. The missing validation allows me to end this when I want to, and not only when I can reach the magic number using my position and the role. And it works if I make a few moves and then reach the magic number. At that point, I get the message. So the overall structure of this program is written. Now, like every good chef on a cooking show, I have a version set aside that has those functions written. I'm not going to go through writing them in this video because the purpose of the video is to solve a problem using functional decomposition, and I don't want to make it longer by going through those functions. You might work on them for practice, and I do recommend thoroughly testing the validation function independent of the program, as that is a somewhat complicated function. But here is the final version of the program running. You can see that the gameplay can be quite frustrating, as you can dance around the magic number for a very long time. I think the game could be improved by having multiple magic numbers and allowing the player to reach any of them. You might think of other improvements. And that is this problem solved. Being able to break the program into functions makes it easy to develop a small piece at a time and to leave difficult problems for later by putting function stubs in their place. You might try writing the two missing functions, and you might also try enhancing the program to have better gameplay. Having more than one magic number is one option. Allowing the player to use more arithmetic, for example, including exponentiation, is another option. You could also implement the alternate functional decomposition, or try another. I'm sure you can think of other variations. You now have written a complete program requiring functional decomposition. I recommend that you close your script window, open a new one, and rewrite the program yourself from scratch. Check back with the video or the program you wrote earlier only if you get into trouble you can't get out of. Once you've completed that, you're ready to move on to solving your own programming problems using functional decomposition.